Today I will talk about the ReCon, a system that helps average user to review and control their personal information leaks in the mobile network devices. So the motivation is pretty simple. Nearly all of us carry mobile devices in our pockets. They are equipped with rich sensors and ubiquitous connectivity. And we use them to access the internet to do a variety of things. Everything from checking social network to shopping to banking. And while we are doing this, we review all kinds of information about ourselves. Now, some important issues arise given this. For one, what kind of information are actually being sent out over the network? Where does it go? Is there anything we can do about it if we are not okay with what's happening? To take a look at this initially, we did a manual test for the top 100 apps in each OS, Android, iOS, and even Windows phones. Basically, we preloaded the device with information that is very conspicuous, play with these apps, and try to find out what information is being sent over the network. So the reason I did this manually, spend weeks of my life, is that we can have more realistic interactions and thus better coverage of the PII leaks than all existing automated tests. Here is what we found. The x-axis is different types of PII leaks. The y-axis is the fraction of apps that are found in each OS that is leaking PII. And all the information, all the leaks is sent in plain text in this chart. So the first thing to notice is device identifiers such as IMEI and geographic locations are by far the most commonly leaked PII. So this run-of-the-mill tracking is perhaps not surprising. It certainly is extensive. What's more concerning is the level of very personal identifiers. Email addresses, real name, gender, relationship status, and even credentials such as our username and password are all sent in plain text to the internet. So what we can take away from the initial study is that PII leaks are pervasive across all mobile platforms and for the most popular apps. Why do this issue persist, even though we've been studying mobile privacy for years? We argue that the mobile ecosystem consists of walled garden inside gated communities, where the walled garden are the locked down OSs and the gated communities are the carriers. So one way to try to address privacy is inside the OS. For example, you can build information flow tracking into the OS. That sounds great, except OS vendors won't do it because it means increased battery consumption or lower performance. Of course, researchers can try to modify open source OSs, but this generally, if users want to adopt them, they generally need to root their phones, which is historically a large barrier for adoption. You can also imagine improving privacy on the network traffic, but one generally cannot tap the network traffic from a phone without looting it, and good luck convincing mobile carriers to deploy your experimental system in their production networks. Though these challenges may seem daunting, we observe there's a unique opportunity, the virtual private network. Almost all mobile devices nowadays support VPNs, generally to support enterprise customers. And instead of tunnel traffic to a private network, we use it as like a VPN proxy. And in the proxy, we can record, analyze, and potentially block traffic that contain personal information. Okay, so VPN gives us access to the network traffic. And this allows us to detect PII as we've done in our initial study. It's independent of any OS or app store. And another advantage is that it's trivially easy to detect the PII if you know what to search for. However, we don't generally know users' PII, and it's not reasonable to ask them to provide it. And in some cases, they won't even know this information, for example, IMEI number. So the key question we must address is how do you find the PII without knowing it in advance? Our hypothesis is that those leaks have distinguishing characteristics. For example, in an HTTP request, if you see something like user ID equals ReCon, they are very likely to be the PII. Would a simple solution like searching for user ID be enough? The answer is no. So in our experiment, this leads to high false positive rate and high false negative rate. The reason is that different strings means different things for different apps, and we can this simple row matching won't work. So instead, we need to learn these structures, and our approach is to build machine learning classifiers to learn these various structures and reliably detect a personal information leak. And one of the nice things about the machine learning is that it doesn't require us to know the PII in advance, and it's resilient to change in the PII leaking format over time. So how does ReCon work? First, we have the machine learning component that identifies PII leaks. We train it to use labeled network flows from our manual and automatic test. And we use it to predict in real time on the new traffic. In addition, our system also collects user feedback from users about whether our prediction is right or wrong, and we use it to continuously update our classifiers. So this machine learning component only requires access to the network traffic. And in our current system, we get this by using Meadow, which is a VPN proxy that is connected to software mailboxes. So we use VPN to inspect the traffic, make predictions on the fly, and interpose on the traffic based on users' preferences. And in addition, users can interact with our system through a web-based UI to manage their privacy. In this work, there's a number of key questions related to using machine learning for PII detection. Unfortunately, I won't have enough time to go through all of our results, and I encourage you to read our paper. In this talk, I will focus on the training, the accuracy, comparison with existing tools, and the result in our deployment. So let's start by answering how do we train a classifier. As I mentioned before, I used labeled network traffic for our control experiment to train our initial classifier. So we observed that the PII detection problem is very similar to text classification problem. Assume that you have network flows like this. There's a request path with a list of parameters. The question is, how do you distinguish information that is generic and not specific to you from those that is actually your personal information, like my name and password? To do this, we use bag-of-words model to extract the feature set for training, which means we break each network flow into a collection of individual words. And with all the available labeled network flows, we extract the word, count the occurrence frequency, and this can potentially give us thousands of features or more, which is both costly to analyze and can lead to overfitting. To address this, we apply a threshold-based model to filter infrequent words like session keys and values that are specific to one user. Here, ID, name, some password are filtered and will not in our feature set. Initially, we train all classifiers, we train one classifier for all the data, but this is a problem because different data collection libraries leak PII differently, and so we use the intuition that the data collected by the same company probably use the same set of API, then thus leaking format similarly. As a first of order approximation, we use their domain names to represent these companies and train classifiers separately for each domain of each OS. Now we've covered our classifier, let's say how well they do. So we use 4 metrics to evaluate the accuracy of our classifier. The first one is correctly classified rate, which is the number of correct prediction out of all the samples, along with false positive rate, false negative rate, and the last metric is the area under the curve value. At a high level, it measures the classifier's predictive power. The value ranges from 0 to 1, and where the 1 means perfect prediction. So all of our evaluation use tenfold cross-validation. First, let's look at the correctly classified rate. For the general classifier, which is one classifier for all the data, the accuracy is 80%. This is okay, but can we do better? Let's look at by testing how well our per domain and OS classifier work. We plot the accuracy using a CDF, where each point represents the accuracy for a single OS and domain classifier. And we've tested with a bunch of different machine learning algorithms. Here we only show the subset of our result. The worst case, naive Bayes, and the best case, decision tree. So if the curve is closer to the right part of the graph, it means the accuracy, the classifier have higher accuracy. And as the figure shows, decision tree performs quite well. Another common approximation is to use ensemble approaches. So we did that, and we find that these approaches have similar accuracy, but they take much more time to train. So we decided not to use them. If we look at the optimization by using per domain classifiers, the vast majority of the domains have better accuracy than using the general classifier. And in fact, 60% of them have zero error. So the key takeaway here is that decision tree classifiers can provide us high accuracy for most of our per domain and OS classifiers. And we see similar good result for the area under the curve value. As I mentioned before, this measures the predictive power of a classifier. So where 1 means strong predictive power. And you can see from the graph that most of the values is near or close to 1, near or at 1. Last, we have found the low false positive rate and low false negative rate. In fact, most of the classifiers have 0 false positives and false negatives. Now you may wonder whether our classifiers actually learn anything about PII leaks. Well, one great thing about decision tree is that they are very interpretable, and we find that they make sense. Like in this graph, the two red paths indicate a network flow contains PII, while the others indicate no leaks. So as you can see, this multi-level decision tree can help distinguish keywords like AUID that is sometimes but not always associated with certain leaks. So at this point, I may have convinced you that machine learning works well, but how does it compare to existing tools, like, for example, information flow analysis, or IFA? IFA offers several advantages, such as being resilient to encryption or obfuscation, and no false negatives. Since there are already several IFA tools existing for the Android devices, we use them to test on all the apps that have network flows from our control experiment. And then we compare the number of apps that are found by each tool as potentially leaking PII. So first we compare the ReCon with the dynamic IFA and JUBIS, because they are the only two that generate network traffic. And here is what we found. The x-axis is different type of PII. The y-axis is the fraction of apps that are found by each tool as leaking PII. We can see that ReCon outperforms and JUBIS in all categories, except the contact information. But here the cool thing, as JUBIS provide us labeled network traffic, we can use it to retrain our classifiers. And we did that. We find that ReCon successfully identified all the leaks that are found by JUBIS. The key point here is that ReCon is not an either-or approach. Instead, it learns from the best of other approaches, and as long as they can provide us labeled network traffic. We also compare ReCon with static and hybrid IFA. In these cases, they don't generate network traces to compare directly, but still, ReCon find more instances of leaks. This is especially true for user identifiers, where IFA tools don't know a username and cannot taint the information. Now I've shown you that ReCon outperforms existing tools in the lab. Let's talk about how ReCon actually works effectively in the real world. First, we have data from an IRB-approved user study where there are hundreds of Android and iOS users is actively using it. So we surveyed a subset of our users, and most of the respondents found the system useful and changed their behavior. for example, stop using certain apps as a result of our user study. And the system so far have found over 20,000 cases of PII leaks, among which we saw crazy things like over 100 cases of credential being leaked in plain text. This came from 24 apps, including popular apps like Match and Hypocrites that are used by millions of users. For these apps, we did a responsible disclosure and gave developers 3 months to fix the problem. So far, only 14 of them have fixed this vulnerability. So to help inform the non-users, we regularly update an anonymized report of the PII leaks for both app and mobile browser in our website. To wrap up, our work addressed the lack of transparency and control over the PII leaks in today's mobile devices. And we did that by learning how PII information is being leaked, crowdsourcing to help continuously improve the prediction, and also allows users to block or change what is being leaked. Our analysis code is open source, and all the anonymized data is publicly available. And with that, thanks for listening.